Hello, pre-calc people. So I was not able to do the Zoom video, so I'm just going to make a short video of this third page because you already have a video of the first two pages. So when we are doing a vertical asymptote, the way you find it is you set the denominator equal to 0 because you can never divide by 0, and that then leaves that vertical asymptote in your graph. So for an example, if I had y equals 3x over x minus 1, first I would look to see if I can cancel any factors, which in this case I can't, but I look at my denominator is x minus 1, you set it equal to 0, so x equals 1 is a vertical asymptote on the graph. Okay. For the removable discontinuity, what you actually want is you want something that is going to be removed. It leaves a hole in your graph after you've removed that factor. So it is the 0 of a removed factor. And we'll do an example, because the original did have that problem child in it. So for an example, if I had y equals, and I'm going to give it to you in already factored form, because that would just make it a little bit shorter here, x plus 2, x minus 3. So when I look at that, I see I can sort of cancel the x plus 2, and that would simplify this into just 1 over x minus 3. So we have to somehow represent the fact that in the original function, you had something that would have made your denominator 0. So we take that removed factor of x plus 2, you set it equal to 0, and that tells me that at -2, I'm going to have a hole on my graph. So it's kind of like the last thing you do when you're done graphing. You go back to where the graph is at x equals -2 and just make a little circle at that spot. This one also, in the final version, the simplified, still has x minus 3. So this one would also have a vertical asymptote at x equals 3. And then we get into our horizontal asymptote. This one is a little bit more, because I want to give you all the cases here. And the easy way that I always talk about it is kind of, because this actually pertains to when you go into calculus, the first thing you're going to do is look at limits. And the easiest way, so that you can do it, I kind of like to give you the shortcut, is if you can determine on the powers of x, is it heavier on top, heavier on bottom, or do you have the same power of x, top and bottom? So what I would do is if it's top heavy, then that means, because again, a horizontal asymptote is what is your x value doing as it goes out to infinity. So as x is approaching plus or minus infinity, what is happening to the graph? Well, if it's top heavy, it's growing without bound. There is no horizontal asymptote. So for an example, if I just gave you y equals x squared, because I could put this over 1, so it's heavier, the power of x is heavier on top. There is no horizontal asymptote. It's growing without bound. If it's bottom heavy, in other words, your denominator is growing really big, well, remember that fractions work inversely. So as the bottom is getting bigger, the overall value is getting smaller and smaller, and it's basically going to 0. So anytime you are bottom heavy, your final asymptote will be the x-axis, or y equals 0. So a real easy one, y equals 1 over x. And so this horizontal asymptote would be y equals 0, always. So that one will always equal 0, which in other words is the x-axis. And then lastly, let me try and get a different color in here. If you have the same power, that's when your horizontal asymptote kind of moves around. So what you're going to do And it depends. You're going to get some value. That value is based on the coefficients of the x, the highest x. All right, so let's look at an example of this one. So if we have y equals, let's say I had 8x minus 2. Oh, I should have done something I could have. No, I think that's okay. Over x plus 1. So what I would do, I can't remove any factors, so I have a power of x on top that is the same as the power of x on bottom. What I'm going to do is just look at the coefficients in front of those x's, and that gives me a horizontal of, whoops, I should say y equals 8. Let me clean that up a little bit. Okay, so this means that I have a horizontal asymptote at y equals 8, because those are the coefficients. So you're ignoring everything else. Think about you're plugging in, let's say x is 1,000,000, because you want to be way out on the horizon, plus or minus 1,000,000, doesn't matter. So 8,000,000 over 1,000,000 basically reduces to 8. The minus 2 and the plus 1, when you're talking really huge numbers, they're not going to change anything. So that's how that concept works. Okay, so now let's do a couple examples to see how this plays out. The first thing you should always try and do is factor, factor, factor. So in this first example, notice I can factor out a 3, and by doing that, it gives me a removable discontinuity. This all simplifies then to 1/3. So I have no vertical asymptote, because there's nothing in the simplified version that's a problem. However, I have a removable discontinuity at x equals -2, and I have no value of x in my final equation, so my horizontal asymptote doesn't exist, because that's just going to be a constant, 1/3. Then in this next one, number 2, notice that it is top heavy. However, I do have a problem child in my denominator, so I have a vertical asymptote at x equals -5. I didn't remove any factors, so there's no removable discontinuity. And for the horizontal asymptote, since it is top heavy, it is growing without bound. There is no horizontal asymptote. Okay, so then let's try number 3 here. Ooh, look, I just made it really big. I'm going to leave it like that for a second. Kind of move it over if I can. On number 3, notice I can simplify this, and so that we have 1 over x plus 4. So I do have a vertical asymptote at x equals -4, but I removed a factor, so I have to give the 0 of that, so that's going to be at x equals 1. And now in my simplified version, notice that I'm now bottom heavy, because I have a power of x on the bottom, so that's going to be y equals a -4. It's really important you also include the x equals and the y equals when you're doing these, otherwise it doesn't make sense, because it's actually the equation of a line, kind of a dotted line. It's a border that you're establishing. And then this last one, okay, so there's nothing to simplify, which means I'm not going to have a removable discontinuity, but I see that I have 2 discontinuities because I have 2 factors here. So I actually have 2 vertical asymptotes at -9 and at a +2. I didn't remove anything, so I have no removable. And because it is bottom heavy, this does mean that my horizontal asymptote is going to be at y equals 0, basically the x-axis. Okay? So that's how you would go about doing those. Now these last ones is kind of just an overall review of the kind of functions that we looked at in the past video. So for x to the 1.5, what kind of function is that? So since it is a variable raised to a power, we call this a power function. And because that 1.5 is greater than 1, its characteristic is that it is an increasing function. On number 2, now your exponent is the x, so that's exponential. That's kind of how you tell the difference between these. And because 0.7 is between 0 and 1, this one is exponential decay. And then our last example here, x over x minus 3, that's going to be your rational algebraic, because you have a function on top and a function on the bottom. And the characteristics of this are, we know we'll have a vertical asymptote at x equals 3, because that's what makes the denominator 0. We did not remove any factors, so you don't have a removable discontinuity. But your horizontal asymptote, you do have the same power of x on top and bottom. So that's going to give you the line y equals 1. All right? So that's kind of how you find the discontinuities and the characteristics. Now what we're going to look at is something that all functions share. All functions are going to have domains and ranges, and we want to be able to identify those and also graph functions within restricted domains, because in the real world, functions don't always keep going forever and ever and ever, because you're usually within some sort of a constrained system. So we're going to look at this. Notice it is a parabola. F of x equals negative x squared plus 4x plus 12 with a restricted domain here. So the best way to graph this, I think, is to start at the endpoints and figure out what those. So I make a little input-output table. If I plug in -3, and at this point you can either use your calculator or Desmos or whatever you have available. If I plug in a -3, I get the opposite of 9 minus 12 plus 12, which leaves me with just the opposite of 9. So I know that at -3, and I'm really picky about, I do not count tick marks. You guys need to label those axes with your points. So 1, 2, 3, 4, 5, 6, 7, 8, 9 is way up here. But that was a -9, so I caught myself there. All right, so this will be our -3, -9. And then our next point is the other endpoint. I'm going to leave a space here because it is a parabola, so I'm going to find the vertex in a minute too. So if I plug in the other endpoint, the opposite of 64 plus 32, -32 plus 12 gives me a -20. And I just remembered, I always forget this, I have to do my y's by 2, otherwise it's not going to fit. So this was 18, this was -18, -20, so 2, 4, 6, 8, 10. So -9 is actually right here. Sorry about that. I always forget that. So 8, 1, 2, 3, 4, 5, 6, 7, 8 is right here, and 8 is at -20, just a little bit off the chart. Okay, now what we need to do, because this is an upside down parabola, because your a value here is negative, so we know it's a, what we call a frown. Hi, you called me right in the middle of my explain everything. It's okay though. No. I was right at the end. It's okay. You know what? I am at the point right now, like I did this on my back to school night video as well. Like if something interrupts or something, I'm like, fuck it, I'm not redoing this. They're gonna see the interruption. I'm not even gonna worry, it's no big deal. I just thought it was funny, because I meant to hit decline and I hit accept, because then we were gonna start talking on the, been funny. I know. I need to turn off notifications on my iPad because it's like, ah. But the kids always like it. They're like, when the dentist calls, it's like, take the message, take the call, take the call. Yeah. Mm-hmm. Uh-huh. Oh yeah, it's all the same. You know what? Why don't you just, I'm sorry, I'm just trying to cut down on work for me, and I don't really care about past stuff, so I just stole Harriet's dosaries. I mean, sometimes I'll do my own, but sometimes if it's something I've already taught, I just pull it in. They already have it. Just download theirs, put it into Studio, and then embed it to save yourself some trouble, you know, if you want to save some time. And I don't even care whether it's not my bare bone notes, but it's got it's got more in there, which might even be better if they weren't there, because you're not doing the full blown out explanation. I mean, that's just to tell you the truth, because I'm gonna go crazy otherwise. I can't do and I'm not very good at recording the Zoom while I'm teaching, because there's so much other crap going on, letting people in and checking the chat room, and you know, then they go to the breakout room, and I sent them to a breakout room in A2A, and then they're all gone. I'm like, okay, kill me now is what I said, and I'm like, oh shit, I'm still recording. Yeah, yeah, yeah. Yeah, actually, that's why I was starting to do it. I was doing one for pre-calc as well. Yeah, I was going to make Mondays. What is it? 1.3 because they have to. Oh, okay. No, I don't care. How do you share them if you do it in Canvas? Oh, the shared folder. Okay, and then I can just download and I put it in my studio. Okay. I embed it. Yeah. No, it's really easy. Yeah. Yes. Okay. Yeah. Sure. Yeah. Yeah. Definitely. Yeah. I know. Are you staying sane? Because. Oh yeah. 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 Mm-hmm.